Welcome to the explainer. You ever wonder about that tiny pause, right before an electronic device actually shuts down? Or when a light kind of dims out instead of just snapping off? Well, believe it or not, that's not bug, it's a feature. It's all thanks to something called first-order circuits. And today, we're going to dig into exactly how they work.
Yeah, I mean, you've definitely experienced this, right? You flip a switch and the change just is an instant. Maybe a speaker makes a little pop or an LED slowly fades to black. So, what's the deal with that moment of hesitation? What's really happening in there? Well, like I said, that delay isn't some kind of mistake. It's actually a core property of these specific circuits. See, in a super simple resistive circuit, electricity is basically instant, on, off. But these circuits, they're different. They have parts that can actually store energy. And because they can store energy, it gives them a kind of memory of their past state. So they don't just react instantly, they react over time. Okay, so this whole idea of memory is really the key to everything. Because the circuit remembers where it was. It doesn't just snap to a new state, it transitions. It moves from point A to point B. And that transition, that's what we see and feel as a delay. So let's meet the components that are actually responsible for giving these circuits their memory.
All right, first up in our lineup, let's talk about the capacitor. This is one of the main players responsible for that delayed reaction we've been talking about.
So at its heart, a capacitor is just a device for storing energy. Technically, it stores that energy in an electric field. But honestly, the best way to think about it is as a tiny rechargeable bucket for electrons. Super simple. And to make this super clear, let's just run with that water bucket analogy for a second. The capacitor, that's the bucket itself. The voltage, that's the water level, the pressure. And a resistor, which is just something that slows down the flow of electricity, well, that's like a drain pipe. How fast that bucket empties totally depends on how big that drain pipe is. But here's the really important part. This whole emptying process isn't random at all. It's incredibly predictable. When you take a full capacitor and hook it up to a resistor, it discharges in a perfect mathematical curve. And this has a name. It's called the circuit's natural response. Why? Because it's just what the circuit naturally does on its own, with no outside power source involved. Okay, so we get it. The bucket empties. But how fast? Well, it turns out that's governed by this really cool universal rule that basically defines the entire personality of the circuit. And the answer to that question isn't just some random number. No, it's a fundamental property baked right into the circuit's DNA.
It's called the time constant, and we represent it with the Greek letter tau. So what is it? Well, it's the specific amount of time it takes for the voltage to drop down to about 37% of whatever it started at. You can literally think of it as the circuit's built-in speed. And for a simple capacitor circuit, the math is super easy. You just multiply the resistance R by the capacitance C. Now check this out, because this is pretty interesting. The decay isn't a straight line, not at all. In that very first time constant, that first chunk of time, the circuit loses more than 60% of its voltage. But then, in the second time constant, it loses a way smaller piece. The change actually slows down the closer it gets to being empty.
And after 5 of these time constants have passed, the voltage is down to less than 1% of where it started. So, here's a little rule of thumb engineers use all the time. After 5 tau, we just consider the capacitor fully discharged. It's close enough. And what's really cool is that this whole idea of a time constant, it's not just for capacitors.
All right, time to bring our second character onto the stage, the inductor. It also creates a delay, just like the capacitor, but it goes about storing energy in a totally different way.
And this really shows the difference perfectly. If a capacitor is like an energy bucket that doesn't like changes in voltage or water level, an inductor is more like a big, heavy flywheel. It stores its energy in a magnetic field, and it absolutely hates changes in current. Think about it. It has inertia. It takes time and effort to get that flywheel spinning, but once it's going, it really wants to keep going. And its time constant? We find that by dividing its inductance, L, by the resistance, R.
Okay, so up to this point, we've only talked about these things losing energy, right? The bucket emptying out, the flywheel slowing to a stop. But what happens when we do the opposite? What happens when we suddenly hit them with power?
Well, that has a name too. It's called a step response. And instead of discharging, now everything is charging up. The water bucket starts to fill, the heavy flywheel starts to spin up to speed. It's the exact opposite process. But, and this is the cool part, it follows a really similar pattern. And here is the most beautiful, elegant part of this whole thing. The time constant, that tau value, it's exactly the same whether the circuit is charging up or discharging. The very same number that tells you how fast the bucket empties also tells you how fast it fills. It's perfectly symmetrical.
And because of that perfect symmetry, it means we can actually use a single universal formula to predict what the circuit is doing at any moment in time. It's incredibly powerful.
It's like a simple recipe. To figure out the voltage or current at any given moment, you just need 3 ingredients. You need to know where it started, you need to know where it's eventually going to end up, and you need to know the circuit's time constant, tau. And boom, here it is. This is the formula that describes that entire journey from start to finish. I know, it might look a little intimidating with the e and the exponents and all that, but it's just a fancy way of saying what we already know intuitively. It's just saying that the value at any time is a mix of its final destination, its starting point, and how fast it's traveling, which, of course, is our old friend tau. That's really all there is to it.
So, from now on, the next time you see that little electronic delay, you'll know it's up. It's not a bug, it's not a flaw, it's the beautiful, predictable physics of energy storage doing its thing. And this little managed delay is actually what makes so much of our technology work, from the flash in your camera to the timing circuits that run our computers. It's all just the hidden story of the energy bucket and the flywheel, working away silently inside almost every single device we own.